phasor diagram is used to illustrate the phase relationship between V and I, the voltage and the current. So let's just try and put this into test by putting it into a pure R circuit, pure C circuit, and pure L circuit. So for pure R circuit, where you connect just a resistor to an AC circuit, you see that the V and I are in phase. So V and I are in phase means the phase angle should be equals to 0. So if you draw it, translate into a phasor diagram, you should see that the V and the I should be pointing in the same direction, and there should not be any angle between I0 and V0 phasor. So moving on to pure C circuit, where you connect a capacitor to the AC circuit, you see that the V lags I by 90 degree. So you see that the peak for V is happening later compared to the peak of I. So I is happening earlier, V is happening later for the peak. So in this case, you say V lags I. So V lags I by 90 degree. So because it lags, then therefore the phase angle is negative 90 degree. So if you translate that to a phasor diagram, you see that the phasor diagram is actually lagging behind current, because both the current and the voltage phasor, the I0 and the V0 phasor, both of them will be rotating anti-clockwise. So if both of them are rotating anti-clockwise, you see that the I0 is actually leading the rotation, whereas V0 phasor here is lagging behind in terms of rotation counterclockwise. So if you try to measure the phase angle is again the angle of V0 with respect to I0. So the angle should be measured from I0 to V0. From I0 to V0, we see that it's a clockwise angle. So in that case, it's opposite to our natural rotation, which is anti-clockwise. So therefore, the phase angle should be negative pi/2. Okay, so for pure L circuit, where you connect an inductor to an AC circuit, you see that V leads I by 90 degree. Why do we say so? We see that the peak for V0 happens earlier at t equal to 0 compared to the peak for I0, which happens later than t equals to 0. So in this case, since V0 happens earlier than I0, so the V is leading the I. Okay, and we know from here that it's 90 degree. Okay, so if you translate that to a phasor diagram, you see that the V0 phasor will be leading the I0 phasor. So both of them are rotating counterclockwise or anti-clockwise. So you see that V0 is actually leading I0. Okay, so how do you determine the phase angle between V0 and I0? Again, you go from I0, then you draw the angle towards V0. You see that this angle is in anti-clockwise direction, so the phase angle should be positive. 0 degree and 90 degree that we have mentioned in these three phasor diagram here, I mentioned that they are actually quite easy to be illustrated in a sinusoidal graph. So what's the point of drawing phasor diagram then? Well, I mentioned last time that there are angles which the phase relationship is more difficult to be expressed in the sinusoidal graph. Let's say 30 degree, 5 degree, or even 70 degrees, let's say. These kind of angles, which are not 0 and 90 degree, can be quite difficult to be expressed using two sinusoidal graphs like this. So it's better to express them using phasor diagram. But is it possible to create those kind of phase angle, 30 degrees, 70 degrees? Yes, those kind of angles are actually possible to be created. How do you create it? By combining different circuit elements in an AC circuit. Our discussion here has been pure R, pure C, and pure L, where you connect only one circuit element to the AC circuit. But if you happen to have an AC circuit which connect multiple circuit elements, like R and C together, or R and L together, or RCL together, then at that moment your phasor diagram will be more complicated than just 0 degree or 90 degree phase angle. So let's try that on a few questions. A 12 kilo ohm resistor and a 0.50 microfarad capacitors are connected in series with a sinusoidal AC supply of angular frequency omega equals to 100 radian per second. So it mentions here that you have a resistor and you have a capacitor. And both of these circuit elements, we call these counting circuit elements, are connected in series. Okay, so I'm drawing it in series and they are connected to a sinusoidal AC supply. So let me draw it out everything. So this trigger with a circle here represents an accumulator or an AC power supply. Okay, so let's label everything down. The resistor here, R, should be equals to 12 kilo ohm, whereas the capacitor has a capacitance of 0.50 microfarad. Then the sinusoidal AC supply has an angular frequency of 100 radian per second. Okay, means by oscillate back and forth, the current and the voltage oscillates back and forth with a frequency of 100 radian per second. And RMS current in the circuit is 5 milliampere. Okay, so this is the circuit that we have. So in question A, they asked to find for the RMS potential difference across the resistor. Well, you know IRMS. If you are asked to find the VRMS, then you know that the relation should be something like V equals to IR. But for this case, it's resistor, yes, so it's V equals to IR, like what we said just now. So IRMS, we know that to be 5 milliampere. So 5 times 10 to the power negative 3, that's IRMS. For resistance, our resistance is 12 kilo ohm. 12 kilo ohm. So if you multiply these two things together, you should get 60 volt as your RMS voltage across the resistor. So this is what you get if you put a voltmeter across this resistor over here. Then your answer will be 60 volt. Okay, so moving on to question B. Question B asks for RMS potential difference across the capacitor. So for B, what you do is you connect a voltmeter across this capacitor and you try to determine the value. So the value that you determine using a voltmeter will be the RMS voltage across the capacitor. Okay, so let's try to find what's the RMS potential difference across this capacitor. So again, it's VRMS equals to IRMS. So what's the ratio between VRMS and IRMS for a capacitor? That's our capacitive reactance, XC. Okay, we know that capacitive reactance is equals to omega C, yeah, and they are below, okay, 1 over omega C. So knowing that, I think everything is here. You can just do substitution. IRMS should be 5 milliampere. Then we have 1 over our angular frequency is 100 radian per second. Our capacitance is 0.50 times 10 to the power of negative 6. So from here, if we do our calculation, I think you get 100 volt as your answer. Okay, so your answer for across this voltmeter should be 100 volt. Okay, the next thing is, what's the RMS value of the sinusoidal voltage? RMS value for the sinusoidal voltage. So that should be what you measure across the AC power supply. Okay, so if you put a voltmeter across here, then that's what you will obtain for your answer at C, the RMS value for the sinusoidal voltage. So the sinusoidal voltage is the overall voltage across the AC circuit. So to determine this thing, you will start to use the concept of phasor diagram.